TKP1, TKP2. So sorry. So here you can see we are doing it duplicates, and now I will start sticking the films on it. So I will show in one while how we are doing it. So we are starting with this TKP1, and we'll take TKP films. So in this one, we have to make sure that this our shiny part or our upper part of the film, when we cast it in this any surface, there is one shiny part, one rough side of the film. So we have to make sure that the shiny part should be on the upside. So we'll use dendrite for that. So we have to make sure that we should use dendrite as less as possible. So we'll use spatula for that. We will not directly place from this tube. I will take it in a small spatula. Then I will. Yeah, just a small amount we will take, and then we will keep rubbing it on the surface of this glass vial perimeter. So while it's happening, I will tell you that before they start the experiment, we have to measure the inside diameter of this glass vial using any vernier caliper. So that area will be in this equation or formula. So that will also go in this formula. And another thing that just like in the yesterday, you have seen that how they have measured this thickness of the film for the mechanical properties. So for this, the piece we have cut for this experiment for water vapor permeability, we have to take few readings from that, like 4 or 5 readings from different places of the film, and we have to take an average. So we will know what is the thickness of the film. So that thing should be also be considered in this formula. So we have already done it. So you have already seen how they have done this thickness measurement in the yesterday session. And for this inside diameter of the glass vial or cup, you can use vernier caliper. So now here I'm placing just dendrite on the surface, and we'll just rub it. So it's almost like dried only. So it will not transfer any moisture in the film. So it will not uh, gain any moisture. So now I will place it. After this, we will leave it for some time so that the glue can do its work, and it will be stick on it properly. And similarly, I will do for every glass vial with this respective films, whatever they have mentioned in this glass vials. So if uh, if the films are very brittle, you can keep some weight on it for some time, so it can stick very easily. And the next one you can see here, I have done for all these things, all these glass vials in the similar way we have done it. So now this still there's like we have stick it on this mouth, but still if we have some doubt that there may be some passage between this film and glass vial, so we have to make sure that this should not no air, no environment should affect this should transfer from the outside to inside or inside to outside. No air should be transferred. So we will just keep it like this, we'll fold it like this, and then we will seal it with the sellotape. So in this one, you can see, I will just seal it with the sellotape. So we are using this glass vials or different cups for that, but there are some WVTR cups also, which are available in the online website, but those are very costly. So in this way you can do like in any lab you can do, and the only thing you need a weighing balance or some chemicals only. So you can do in that this way also. So here, look, I have just closed all the way, all the possible ways for the air to transfer, except the area, the inside diameter of this glass wire, so that this when we'll calculate it, there will be mostly no errors on that. So you can see here this now everywhere it's sealed except this opening, because the opening is only should be sealed with this film. Now in a similar way I will do for every this glass vial. So in a similar way, I will do for everything. Yeah, you can see it now. Now I've done for every glass vial and every system. Now this whole system will be weighed. It's not only the film, it's not only the cup, but the whole system. This will be weighed, and this will gain this whole system. This one glass vial, the system will gain the weight in per hour or per day. You can decide as you like, as you are getting this weight gain. So that thing, the units you can change later also, as per your convenience or as per your comparison with some other like papers from where you are comparing your results. So you can change it later also. But for here, like we are keeping it in hours. So after every 1 hour, we will do that. So you can say now I will take the weight of this whole system, not only the films, not only the cups, but the whole system. This for the TKP one. Now I'll take the weight. So this, for example, I've written it down, 12.2118 grams. And similarly, I will do for every glass oil. So after that, when this thing will start, so it will start gaining the weight because the moisture from outside, 75%, 90, 97%, whatever you have made inside the desiccator, that will be pushed inside this glass oil, and that will pass through the films. So that's why we say this permeability. So the actual water vapor is start transferring through the film inside this glass oil to get absorbed in this calcium sulfate and hydrous powder, so it will start gaining the weight. So now I will show you that how we kept this saturated solution inside this desiccator. You can see some solution is there. So you can keep it like 100%, like sorry, 100 ml or 150 ml. So we have kept here for 100 ml saturated solution, and I've kept it here. Now I will close the lid, and here also you have to make sure that there should be no gap between this lid. So you can use glycerol here. You can use place glycerol on this between this lid and this desiccator. You can place the glycerol. After that also, to make it ensure that there is no air passing, we have just closed this whole thing with the tape, so that there should be no interaction with the outside environment. Now this whole system have now become this one system which is creating a gradient in this water vapor pressure. So this RH gradient will drag the water vapor from the desiccator to inside this cups. So now the next step, we will keep it in some specific temperature. So like here we have kept 37%. So this one, I will keep it inside. Now this will start doing its work as I have explained, that from after every 1 hour, we will take it out, we will take the weight, and then we again place it inside the desiccator, and so on. We will keep doing it. Sometimes people do for the days also, per day, in the per day basis. So they do in like in one day, then after 24 hours, they again take the reading, then so on. So this is the final step. We just kept it. So in the next 1 hour, we'll again take the reading and so on. So this is all about this demonstration. So now I will show you how we are how we are analyzing the data. So I have already one. Okay, so first I will talk about some things like how will change this RH percent to pascals, because generally we are not going to, of course, we are going to give the units in pascals. So this RH, like for example, we know the RH percentage, and so how will change this RH to pascals. So this is the formula that RH, whatever in the percentage, and we need this one, partial vapor pressure. For example, for 75% RH we have made in the desiccator. So what will the pressure value in this Pascal? So for that we need saturated water vapor pressure. So for that we have RH percentage, but we don't have both of this value. We want this value. So for this saturated vapor pressure, so we can go to we can go to some other way. Sorry. Yeah, you can find this in online. This is a weather government site of weather. So this is vapor pressure calculator. So for this specific temperature, you have to know that what temperature you want to know that saturated vapor pressure. So here we will select Celsius. You can, for example, 37 degrees Celsius we have taken. So we can keep it 37. Then you convert it. So here you will get this Pascal value, kilopascal. So in Pascal, it will be 6276. So that will be our vapor pressure in pascals. So I will move forward. So from here you will get, because now we have RH percentage, we have a saturated vapor pressure, and we want this partial vapor pressure. So that we will get from this formula. And this is the formula for water vapor transmission rate. So there is a difference in water vapor transmission rate and water vapor permeability. Actually, the water vapor transmission rate is not giving us a complete picture of the material. So this is the formula. For example, the weight gain delta m upon delta t, that is time into area of the materials. And the unit you can see here, like gram per meter square per hour or gram per meter square per second, whatever you can take in, like as per your convenience. For water permeability, the two major things will be considered that will give the complete picture of the material's property, intrinsic property of the materials, that is thickness of this film and vapor pressure, delta P. If you like just multiply in this one thickness of the film and divide by the pressure difference, you will get the water vapor permeability. So there are the units like you can use for the water vapor permeability, that is gram into meter upon like meter square second Pascal. That's SI unit. The key differences are very clear that WVTR only focus on the rate of water vapor transmission. However, the water vapor permeability shows that the intrinsic material property. So, and it depends upon the water vapor transmission rate, depends upon the thickness of the material, because when you do it for another sample, you will get the different WVTR, but that is not the case with WVP. It is independent of the thickness because it already has been normalized in the formula. So it's not very not explicitly considered in this papers or for the research, but the WVP includes the partial pressure difference also. So driving forces also includes in that one. A unit I have already told you. So next one, I will move to this Excel file. I will tell you, for here we have some data already for like 0th hour and 1 hour, 2 hour, 3 hour, 4 hour, up to 8 hour. We have the data, and if you're not satisfied, you can go up to 12 hour. And if you are like getting too slow weight gain, so you can go for this 24-hour system. You can go on the day basis. So that's also you can do. So here we have taken diameter of the cup. So and a radius of the cup and area of the cup. So you can change it in meters also. So this will be our final area of this inside diameter of the cup. And these are our readings for like in grams. So these are all the readings. So I will tell you how we're doing it. So for this, we have to do that the weight gain. So for that, we have to take as how much weight gain happened in 1 hour. That will be minus in how was the weight on zeroth hour. So that will be the same. For C column will be same for everything. So you have to put the dollar sign here to seize the cell. You just hit the enter and you can place it right like this. So now you can see in 1 hour weight gain was this. In the next 2 hour weight gain, it kept increasing. So okay. So similarly, we have to do we are doing it in duplicate. I will tell you. So like film 0A, film 0B, 1A, 1B, and up to 5. So you can do it in triplicate also. So just to show here, I'm doing it. I'm showing it in duplicate. And similar way, uh, we'll do for all, but we have to change the cell. For example, this one. This should be D4. Yes. 4. Okay. For this one, C5. This one, C6, C7, C8, C9, C10, C11, C12. And after that, you can populate the data like this. So now we have get this delta M we already got, but this is the time, like this time 1 hour, 2 hour, 3 hour, 4, 5, 6, 7, 8, and this is our weight gain. So to know that delta M by delta T, we have to plot something like this. You can go to insert the chart and this one. So now you can see that how the weight gain is happening in every 1 hour. So the most of the cases it happens like in the first 1 hour, 2 hour, or the first 1 day, 2 day, the weight gain is very much. Then it gets lower. So this the reason is because the most of the biopolymeric films which are based on polysaccharides, they are very hydrophilic. So on the first 1 hour, they will the film itself get the weight, they absorb the moisture. After that, it starts transferring the moisture inside the cup. So that if you keep that thing for equally for that thing you will consider for equally for each film, so there is no problem. Otherwise you can start from here also. Some people start from this after this extreme weight gain. After that, when it gets linear or when it gets the slower weight gain, they will start from there. But anyway, we'll start from we'll keep it like this only. For this, you have to just add the trend lines, and you just sorry, double click on trend line. Now you display equation on chart. You check on that and you will get here the slope 0.0517. So you have to write it here 0.0517. And for the next one, you have to do it for the all. So you'll go here, right click on that, select data, then you do edit data. So Y values we have to change for the next one. Okay. Okay. So next one 0.0457. Similarly, 0.0451. Seven, 475, sorry. 475. Select data. We have to do it manually one by one. 0.0441. Once we'll get all the slopes, we'll start with the next finding WVP 0.042. 0.0446. 0.0392. For the last sample, film 5. 0.0245. Zero point zero three double six. Now we have got all the slopes here, that is gram per hour. Okay, all the slopes we got. Now we need area of the container, so that we have meter square we take. So area will be same for each system film, for each film. And for this WVTR, that is now gram per hour per meter square. First, we'll calculate the WVTR, so that if you want to calculate or give your data in WVTR for your convenience, you can use this one also. Otherwise, we will calculate that WVP in the next step. So for this, you just have to divide the slope with area of the container, and you got to WVTR in gram per hour per meter square. So here you can calculate your average of your WVTR. It's better to take 3 samples, and you can calculate standard deviation too. So this will be your WVTR. You can represent your data like this also, but more specifically, you should go like in the WVP. That will give you the complete picture about the materials. So in WVTR also, you can see that this water vapor transmission rate is decreasing slowly, like 34, 32, 30, 29, 21. So it may be because of the more, like film 0 is having the highest water vapor transmission rate. That is bad for this any packaging, any food system. And for like on film 1, 2, 3, maybe like when you increase the concentration of some nanoparticle or mix with some other biopolymers, mixing with some cross linkers that is making more like complex matrix inside this biopolymer structure. So that may not allowing the water vapor to pass through this film very easily. So that's why it's getting reduced. So in next step, we have already calculated the thickness of the film before starting this experiment. So these are here in mm. And the Pascals, we have calculated it that this Pascal is for 97% RH. But in video, I have shown 75% with this data already we had. So we are just showing it for an example. So this is for the 97% RH. You can calculate it for 75% also. There's not any big issue. You can easily calculate it. So just for example, I'm showing it now how to calculate this one. So it's nothing, just you have to put WVTR you have to take is equal to, you should put some brackets before that. WVTR into now thickness divided by, sorry, divided by we are dividing by Pascals. So before that also you keep one bracket because we are going to need it. And now since our uh, this our time unit is till now it's in hours. So in case you want to change it in seconds, you have to multiply divide by 3600, like hour to minutes, minutes to second. You know how it goes. And for this thickness, because the thickness of the film is in mm, so we have multiplied this one is WVTR. So to for that we have to divide with 1000 also to convert the that our units. Now you populate it. So that's how you're getting this WVP values. Now for this average or mean of WVP, and next will be standard deviation equal to average that's the average for WVP for film. Oh yeah, this will be film 0, film 1 as the final value of WVP. Film 0, film 1, film 2, film 3, and film 5. Similarly, for standard deviation, just populate it. So that's the standard deviation for it. So this is the final your uh, final values of WP. You can directly use it in the table, or you can plot it in Origin or your Excel also. So to how we are showing it in papers, we don't show like not showing exactly like this value because like it's getting multiplied with 10 to the power minus 10. So for that, to make it simple, what we'll do, multiply this one with 10 to the power 10, let's say. Let's see how it's coming. Okay. So now we know, but the 10 to the power 10 to the power 10 we have already multiplied. So we have to keep it in mind. So this one you can say WVP into 10 to the power minus 10. That's how we will represent our data. And for this one, standard deviation, you can just into 10 to the power 11. You can keep it like this. Okay. So here you can see this. Uh, these are coming good values. You can represent it easily. This one also standard deviation into 10 to the power minus 11. So, or you can keep it in, sorry, Or you have, if you want to plot it, you have to keep it in the 10 to the power minus 10 also. Both should be the mean value, and this should be the same. So let's say we are just doing it in 10 to the power minus 10. Okay. Just like this. So now you can keep it here. Now you can plot it anywhere. For example, I will show you how we are plotting it. For example, we'll open the origin. Right here, film 0, sorry, film 1, film 2, film 3, and film 5. Okay. Now we cannot directly copy and paste from here. First, we have to make it in number format. Okay. So this will be our final one. I will add one more column to show this standard deviation in our graph. We have to make it as y error. So we'll just right click on it. You go to set as, and you will make it y error. So whatever we'll put values here, that will automatically go to this y error. So this is, I'm going to copy and paste here. Copy, paste. Now I can plot it using some line plus, yeah, line plus symbol. Yeah, now you can see this one. So in this one, you can see that how this water permeability is reducing. Here you can keep WVP in bracket. In bracket, you have to add the symbol into. Okay, let me find it. Okay, just keep it like this, into 10 to the power, not here, WVP into 10 to the power minus 10 we have taken there. In bracket, you have to keep this one, gram meter upon meter square second Pascal. Gram into meter upon meter square per second per Pascal. Now it 10 to the power minus 10 will be considered for both the standard deviation also, or your data also. It already came film 0, 1, 2, 3. So here you can make this, you can just, like in the previous session, we have already told how to make this graph. Okay, so in this line and text will go in the left one. We don't want the minor ticks, none. In the bottom one also, we don't want Any minor ticks? None. Okay. So here you can write WVP of films. Keep it here. Here you can write film types. Okay. So that will be your complete picture. Or in any case, like you are having some like you are doing ANOVA. So for example, for this one, you are using an ANOVA and you have made some standard deviations and doing some significant want to change or want to show some significant change. For example, this for this one you are getting lowest value in ANOVA. You can show the significant difference. A Then, for example, I haven't run ANOVA for this data. Just showing how you can I can make the final graph for your publication or anywhere for presentation. This one also A, for example. This one is B. Let's see. And this one B or A, whatever. B or C, whatever. Like let's say this one is B, or this may be maybe AB or B or C, B or C or A, B or B, whatever. So now this is the complete graph which you can put in your papers. And for this to save this in high quality, you can go here in the file, you can export, open dialog, and you can save it in any format. For example, in I want to save in TIFF format, so I will select in TIFF format, and I can select the location where I want to save it anywhere, and you can give the file name WVP or films, and here you can select the resolution also. The very high quality you can select, and to 1200 dpi. And for the preview, you can see the preview this side. It's not getting dragged. It's not getting rolled in the bottom. Otherwise, I would show it. So that's all. Once you hit the enter button, you will get your graph saved in your system. So that's all about the water permeability, water barrier property of the films. If you have any question, this session is open for the question and answer. Thank you very much. You can now ask the questions. Okay. So what is the role of both chemicals used here? If filled chemicals in desiccator act as best desiccant like silica gel, shall we fill the water inside the glass container and we express how much weight can? Yeah, exactly. You can do it. A lot of people are doing like this. Exactly you have told. Like the only thing you have to make only thing matters is you have to make the gradient. That's you have to make the difference in RH. Whether you use silica, some chemicals, or directly water also. When you will use water inside this desiccator or inside this glass vial, that will be 100% RH. We'll consider it as a 100% RH. So that one also you can use it. So that's good question. What's the role of both chemicals if they feel the same, I think, or repeated question? Okay, in the glass container, it's possibility. Um, yeah, Same thing. If you any other one has any more questions, you can drop in chat box. I will just tell you right away. Okay, I will wait for a few more minutes, like 1 or 2 minutes. On that, meanwhile, you can drop your questions. If you have any doubts, you have any questions, so you can ask here. Okay, so I take it as there is no question. So I will just close the session. So uh, do you consider about the errors, right? Uh, I'm confused with what kind of error you're talking, but anyway, like for example, the errors only that maybe happens when we take out this glass vial after every 1 hour. So there will be fluctuations in this RH percentage in the desiccator. The whole system will be disturbed again. So that is the problem when we do it the hour basis. So that's why most of the people are doing in day basis, so that at least 23 22 hours they will get in the constant RH. So that is one way of error. Another one is when we are sealing this films, so that also is maybe very prone to the errors. So that also we have to see that. And others are like, for example, standard deviation, if you're talking about. So that also can be seen. If you are getting too much standard deviation, you have to repeat it or redo it again. And you have to run the ANOVA to see that where you're getting the like significant difference or not. Any moisture that can be transmit horizontally without passing through the film, is it possible? Yeah, that's what I was talking about, because that's why we kept it right on that, so that there's no possible way that this moisture will go in the horizontal way, like between the film and the glass vial. There should be no escape for this, no passage for this vapor to pass through. So that's why we sealed with this dendrite first, then we again put this tape, sellotape. So there are like mostly like 99.9%. There is no way that the moisture can be passed through horizontally. Okay, thank you very much, everyone. So with this, we'll conclude the session one of this day. I hope you find this session insightful and engaging. A heartily appreciation to all the participants for their mindful listening. After lunch break, we will meet again for session two with an informative lecture by Dr. Pritam Sarkar, Associate Professor of Food Engineering Department, NIT Rourkela. Thank you all, and meet you very shortly after the lunch. So stay tuned with this WhatsApp group. Every time we will share the fresh links, so you have to just join it timely. So thank you very much. You enjoy your break. We'll meet you soon. Now you guys can leave the meeting.